Hello, everyone. This is the lecture for section 3.2, the derivative as a function. So in section 3.1, we defined the derivative at a point. We defined the derivative as the instantaneous rate of change or the slope of the tangent line at a specific point x equal a, okay? In section 3.2, we get to turn that idea, that concept, into a function, okay? And what you're going to see is none of the work that we did in section 3.1 is going to change. It's actually going to be exactly the same, with one big difference is that instead of getting the slope at a specific point, we're going to get a function that gives us the slope at any specific point we want. So we turn something that was just confounded to a point. We're going to now turn it into a function that gives us the slope of the tangent line for any x value we want. Okay. The definition for the derivative as a function is this right here. And notice the only thing that changes is this x used to be an a before, and now it's an x because it's going to be turning into a function. Okay. If we do the same process, we get the equation for the slope of a tangent line at any x value we have. Okay. And then as a definition here, I want to define what it means to be differentiable. Something that is differentiable means you can take the derivative of it, okay? And that's basically this tail end right here. Basically saying that f prime at a value a exists, okay? So a function f is said to be differentiable at an x equal a if f prime of a exists, okay? And it's differentiable on an entire interval ab, right, if it's differentiable at every point. Okay, so without further ado, I want to go ahead and do an example to show you guys what the heck it entails to find the derivative function, okay? We have to start out the same way. We have to do the limit definition. So it's going to be f of x. So it's f prime of x, right? This is always going to be the limit as x approaches, as h approaches 0, sorry, of f of x plus h minus f of x all over h. So I have to forewarn everybody about this. Much of the, many of the mistakes that I see from students that people make is that they do their distribution wrong, that they do their arithmetic incorrectly, okay? It sounds weird, but most of the mistakes that come in that sort of appear in calculus are not from calculus, it's from algebra, okay? So double check your distributions, double check your math, double check your arithmetic. Sometimes that's where people fumble, okay? So let's go ahead and start this. So it's exactly how you would think. So the limit as h approaches 0 of 2, I have my function, okay? X plus h squared minus x plus h minus 1 minus f of x 2x squared minus x minus 1 all over h, okay? I'm going to go ahead and expand all of this as much as possible, okay? This is going to be equal to the limit as h goes to 0 of 2x squared plus 4xh plus 2h squared minus x minus h minus 1 minus 2x squared plus x plus 1 all over. I haven't handled the h on the bottom yet, okay? So I want to stop here for a second, okay? This up to here, usually this is the first step that people go wrong. Something goes wrong. Double check your arithmetic, double check your distributions of your signs, double check your expansion of squares and cubes, okay? Make sure those are correct, okay? So it's at this point where if you look at all the terms that are on the top, it looks very, very nasty. There's going to be a bunch of stuff on the top, right? I like to tell people this: you're doing something right if there's a lot of stuff in the numerator that starts to cancel away. Okay, so that's exactly what I'm going to show you guys is going to happen. So I'm going to do limit as h approaches 0. Let's go ahead and start canceling some stuff out. So the +1, -1. Okay, there's a plus x and there's a minus x. Okay, and there's a -2x squared here with a +2x squared up front. So notice how much canceled. Specifically, this thing in the tail just went away. Okay, and this all reduces now to, so from here, I'm going to go ahead and reduce down everything that went away and everything that stayed. So what's going to get left behind now is the limit as h approaches 0 of 4xh plus 2h squared minus h over h. Now, hopefully you guys can see what's going to happen after this point. Limit as h approaches 0. Everything on top has an h in it, so I can factor out an h. H times what gets left behind, 4x plus 2h minus 1 all over h. So remember that problem from chapter 2? We couldn't just plug in 0 because we would divide by it. But this process got us to cancel out that h on the bottom, so now we get left with the limit as h approaches 0 of 4x plus 2h minus 1. Now there is no problem with me plugging in 0 for h. So this is going to be now 4x plus 2 times 0 minus 1, and this is 4x minus 1. So we have f prime of x equal 4x minus 1. So this means that, so what we just found, we are done here, that given a function, given our original function f of x, right? This is the equation for the slope of the tangent line at any x value we want. Okay, let's try out another example here. So the one below really uses some of the knowledge that that you guys saw in chapter 2. You remember those tricks, the mathematical tricks to find limits? Well, that's what we're going to use here. So in order to find the derivative for the square root of x, we're going to go ahead and do it by the definition. So we need to find, we're trying to find f prime of x is the limit, right, as h approaches 0 of f of x plus h minus f of x all over h. So we need to plug it into here. So the limit as h approaches 0 of the square root of x plus h minus the square root of x all over h. Okay, we can't plug in 0 still, right? Because we'll be dividing by 0. So we need to somehow do some, mathematical voodoo to make that h on the bottom disappear, okay? And the way we do that is something that you guys have already seen. I made you do it in chapter 2. I'm going to multiply the top and the bottom by the conjugate of the top. So it's going to be the square root of x plus h plus the square root of x. And I'm going to do the same thing on the bottom. X plus h plus the square root of x. Okay? If I do that, okay, and if I do it properly, okay, there's going to be a bunch of stuff that happens, and this is going to reduce down to x plus h minus x over h. times the square root of x plus h plus the square root of x. Okay, I'm going to leave that work for you guys to do. This is very crucial that you try to do it. Make sure you keep a track of everything that you're multiplying. Make sure the distributions all work out. Okay, but when you do the top multiplication, you should reduce to the top of what's here, this thing right here. Okay, and when you do the distribution on the bottom, I actually didn't do the distribution on the bottom. I kept it the way it is. Okay, we get left with this right here. Okay, now what happens here, the positive x and the minus x, they go away. So I get left with the limit as h approaches 0 of h over h times the stuff that I just multiplied, x plus h plus the square root of x. And now notice there's an h on the top, there's an h on the bottom. Those cancel. I get left with the limit as h approaches 0 of 1 over the square root x plus h plus the square root of x. Now notice that if I plug in h equals 0, there is no problem. There is no problem with me plugging in a 0 in for h. So then that means this is now equal to 1 over the square root of x plus 0 plus the square root of x, which is 1 over the square root of x plus the square root of x, which is 1 over 2 root x. And we are done. So f prime of x is equal to 1 over 2 times the square root of x. We are done. So this down here is now, whoa. This down here is now the equation for the slope of the tangent line at any x value we want for f of x equal the square root of x. Okay, now I am doing a lot of steps here. There's a lot of steps that I am leaving out that I expect you all to be able to handle. Okay, I'm giving you the reduced version, so please try it out. Go in there and don't just take my word for it. Actually work them out. Okay, that's one thing. And the second thing, if you guys notice for both of these examples, there's a lot of stuff that I needed to do. There's a lot of algebra that I'm doing. Okay, and I'm pretty sure many of you are thinking there's got to be a better way. Turns out there is. In a couple of sections, we will be learning shortcuts to finding derivatives. And once we figure out those shortcuts, you don't have to do this anymore. Yay, okay? But for up to section 3.2, this section right here, if it says do it by the definition of the derivative, you must do it this way, okay? So what comes up next is quick checks. These are quick checks that I'm pretty sure if you guys have done the quick checks from before, these should look familiar, okay? You guys are actually gonna be finding the derivative functions for equations that you've been playing around with now for quite some time, okay? So let me go ahead and move on, okay, to the theorem. So let's say f of x is a function and let x equal a be in the domain. If f of x is differentiable, then automatically we can go ahead and conclude that f of x is continuous, okay? There is a proof, so the book proves this. In the interest of time, I'm gonna go ahead and say it's in the book. Just something that you need to keep your mind on, just keep it in the back of your head. Because I don't want people to confuse differentiability with continuity. They're not the same thing. This tells you one implies the other, okay? However, the reverse is not true. I'm pretty sure some of you guys are thinking, oh, if that means if I have a continuous function, right, then I could be able to take the derivative for it. And that is not the case. And that's the example that I'm going to show right now. Okay, so let's take the function absolute value. Okay, we can see that it is continuous. Okay, just using, we can do it using our two conditions. Okay, or three conditions, right? But let's go ahead and use the working definition that we have. Notice that we can draw this graph, the absolute value graph. We can draw it without lifting our pencil. Okay, so I can go ahead and notice I didn't lift my pencil there. Okay. However, it is not differentiable. Okay, and here's the explanation why. Okay, let's go ahead and take this chunk right here. So for x bigger than 0, okay? If we take a look at the slope of the tangent line here, we're basically computing this thing, right? The limit as h approaches 0, f of x plus h minus f of x all over h. If we compute this, okay, for this function, we're going to get that this is going to be equal to 1. And it makes sense because the slope for this graph, right, is 1. It's going up 1 over 1, up 1 over 1, up 1 over 1. Okay, but now let's take a look at the same idea, but x less than 0. Okay, and if we do the limit as h approaches 0 of f of x plus h minus f of x all over h, we see this, that this is now equal to -1. And that is clear from here, right? We go over 1, down 1, over 1, down 1, over 1, down 1. Okay, and if you remember from limits, from the properties of limits, right? Okay, so then this one's going to be the positive side, and this one's going to be the negative side, right? This limit, the limit as h approaches 0 of f of x plus h minus f of x all over h, this limit is going to be equal to both of these, the one from the positive end and the one from the negative end. And it's going to be equal only if the results are equal, and they are not. So we can automatically see that both of these are not equal. So then this does not exist. Okay. Okay. Something now that we know what a derivative is, right?
Here's a reminder. Take out the garbage.
I hope you guys heard that. Alexa is reminding me to take out the garbage. Okay, let's keep going. So now that we know what a derivative is, it's giving us a pretty nice property of what our graph is doing, okay? So let's go ahead and take a look at this function right here. So what we have graphed right here, this graph right here is this function right here, okay? So we're going to use this blank graph on the right to sketch its derivative, okay? So remember what a derivative is. It is the slope of the tangent line, okay? And if we look at that a little further, we can say that the slope of the tangent line, right, gives us what's happening to our graph. Is our graph increasing or decreasing, okay? So we know from pre-calc that a line is increasing if the slope is positive, and a line is decreasing if the slope is negative, okay? So we're gonna go ahead and try to graph the derivative for this function right here on the left. I'm going to try to graph it on the right, okay? So automatically, I want everybody to take a look, and we're going to notice that there's two real important points. There's one right here and one right here that split up our graph, okay? In particular, I want everyone to notice this, that on this strip, our graph is increasing, okay? And likewise, after this point right here, it is also increasing, okay? And in between the 2 points, we have, whoa, let's thicken that up a little bit. There we go. Between the 2 points right here, our graph is dropping, so it's decreasing, okay? So if we just take a look at those two facts, we can see that since the graph is increasing from negative infinity to -2, that means our derivative's got to be positive, okay? Likewise for 1 to infinity, okay? Since it's growing there, since it's increasing there, our derivative has to be positive, right? Between -2 and 1, since our graph is dropping, our derivatives have to be negative. The slopes of the tangent lines there are going to be negative, okay? And then lastly, at exactly -2 and +1, we can see that our graph sort of like tops out, right? It flattens out. It's going to be switching from increasing to decreasing, correct? So that means the slope at those 2 points have to be 0. Okay, so we've got enough now to graph what we need. So at -2, my slope is 0. So I'm going to go ahead and plot that there. At 1, my graph is 0. Okay. Everything before -2 is increasing, which means my derivative is positive. My slopes of my tangent lines are positive. So therefore, all of these have to be positive. Okay. And then likewise, from 1 on, those are also positive. So those are increasing as well. So that way, that way. Okay. The only strip that's left is the strip between -2 and +1. Those are all negative. So something like this. So there we go. We graphed our derivative. So all we need is really, right, is this fact right here, right, is that if f is increasing, right, then by definition of the slope of the tangent lines, right, then f prime has to be bigger than 0. And then likewise, f decreasing implies f prime is less than 0. That's all we needed there, okay? Okay, let's go ahead and move on. Other notations. So depending on what book you look into, okay, there might be different ways that a derivative is denoted, okay? These are the various multiple ways that a derivative can be sort of written down, okay? Some of these are much more prevalent. Some of these are not too prevalent at all. Some of them you have to look in specific calculus books to really see them. However, they all mean the same thing. You're taking the derivative, okay? So for example, something up front, I think I ordered them in the way that are most common. This is probably the best ways that you'd see them, these as well. And then they go into decreasing order. So these are the ones that you won't see very often, the one in the tail, okay? Carrying that along, we have higher order derivatives. So you can take the second third, fourth, fifth, sixth derivative of a function, okay, that means you're taking the derivative of a derivative of a derivative of a derivative, okay, so on and so forth. They also have various ways of being denoted, and those are here. Likewise, just how I had mentioned up above, some of these are real prevalent, some of them are not too prevalent at all. This one I think is the most common, followed by this one. All of these four I think are the most common in any calculus text, and then followed by these that really don't happen too often, okay? So how do you find the second derivative or the third derivative? So that means you need to take that many derivatives. So let's go ahead and do this next example. Find the second derivative of f of x equal the square root of x. So we already know from our very first example, right? Or example 2, sorry, that f prime of x is equal to 1 over 2 times the square root of x. This is the first derivative. We just need to take the derivative of that thing. So f double prime of x, that is equivalent to the limit as h approaches 0 of f prime of x plus h minus f prime of x all over h, which means we get to use this thing again, okay? So if we do that, that's going to be the limit as h approaches 0 of 1 over 2 times the square root of x plus h minus 1 over 2 times the square root of x all over h. Okay? So notice this one is going to be a, we're going to need to do common denominators here. Okay? And we're just going to do it just on the top. So I'm going to go ahead and do that. So the limit as h approaches 0 of 1. Let me go ahead and show you guys what I'm multiplying here. Come on. There we go. This one's going to be multiplied by the square root of x, because that's what's missing on the bottom for a common denominator. And this one, I'm going to be multiplying it by x plus h on top and the bottom, right? So I get left with this, okay? Square root of x over 2 square root x square root x plus h minus square root x plus h over 2 square root x plus h all over h. Now, this didn't solve anything yet, right? This didn't solve anything because we can't plug in 0 yet. We still have that divide by 0, okay? I'm going to clean it up a little more, okay? I'm going to do the limit as h approaches 0, the square root of x minus the square root of x plus h all over 2 square root x plus h all on top divided by h. Okay, this still didn't solve anything, okay? But hopefully you guys see what's going to come up next. We need to do the common, we need to do the conjugate on the top, okay? And when we do the conjugate on the top, that means I need to multiply the top and the bottom of the top, okay? We need to do the top and the bottom of the top by this. Square root of x plus square root of x plus h all over square root of x plus square root of x plus h. Okay? This will fix it. Okay? This will fix it. And the way that it'll fix it is Okay, there we go. What we're gonna get, okay, is this right here. I'm gonna write it out. H goes to 0, okay? I'm gonna actually write out the entire thing so you guys can see how nasty this looks. Square root of x minus square root of x plus h. Let me clean that up a little bit. Square root of x plus square root of x plus h. Extend that a little farther. There we go. All over 2 square root x square root x plus h times the square root of x plus the square root of x plus h all over h. So this is the part that people get in trouble with. Make sure you distribute that properly. Make sure that your arithmetic is correct, okay? So what happens here, I'm gonna skip a couple steps and I'll get to what's gonna happen, okay? This is now going to reduce to the limit as h approaches 0 of -1 over 2 square root x square root x plus h times square root x plus square root x plus h. So if you actually go ahead and do the entire multiplication out, if you go ahead and do the entire multiplication out, this is what you're going to get reduced to, okay? Now notice what happened again. The h on the bottom disappeared, our problem disappeared. We can now very easily plug in h and not have a problem. So this is now going to be equal to -1 over 2 square root of x times the square root of x times the square root of x plus the square root of x, -1 over, that's going to be x times another, let me write it out, 2x times 2 square root x -1 over 4x to the 3 halves. And we are done. So this tells us f double prime of x is -1 over 4x to the 3 halves. Okay. And we are done. So like I keep repeating, okay, make sure that your distributions are there. Double check them. If you're not reducing it down to here, double check it again, okay? Nearly all of the errors that come out of this process are algebra. Usually when I see students do this, the calculus is perfect. It's the algebra that sucks. So just double check, okay? Okay, let's go ahead and move on. What comes up next is quick checks. I'm making you find the second derivatives of functions that you should be tired of at this point, okay? Let's keep moving on. Last bit. So now that we know what a higher order derivative is, right? So now that we know what the second derivative is, or third derivative, fourth derivative is, right? We're gonna apply it one more time to our, physical science. We're gonna apply it in physics, okay? So we know that the first derivative of a position, right, is its velocity. We found this, okay? So now let's think about it. What would be the first derivative of the velocity, right? So the first derivative of a velocity is the instantaneous rate of change in our velocity. Another word for that is its acceleration, right? So that's what's happening here. We find out that A of t, the common way to write out an acceleration, is the change in velocity over time, right? And that's our first derivative for the velocity, which happened to be the first derivative of the position function. So that means that our acceleration, right, is equivalent to the first derivative of the velocity or the second derivative of its position. Okay, so let's go ahead and try this out. Find and interpret S prime of 1. Okay, so same idea that we had from before. We're dropping a bowling ball off a cliff, okay? And it's given by that equation right here, okay? So first thing, I'm gonna go ahead and find S prime of 1, okay? So that means I'm gonna go ahead and do S prime of 1 is equal to, well, let me find S prime of X first, okay? That's gonna be the limit as H approaches 0 of S of X plus H minus S of X all over H, right? Where we go at it, right? So the limit as H approaches 0 minus 4.9 X plus H squared plus 1,000 minus 4.9 X squared plus 1,000 all over H. I'm going to do some cleanup here. So a negative of a negative, that's positive. And then that turns the plus 1,000 to a minus 1,000. Okay. Automatically, we have a plus and a minus 1,000. Those say bye-bye. So limit as H approaches 0 of minus 4.9 X plus H quantity squared plus 4.9 X squared all over H. We did some of this from before. Let me find it really quick. All right, so this is going to be equal to the limit as H approaches 0 of minus 78.4. Whoops, sorry. Let me go ahead and do it out. Minus 4.9 X squared plus 2XH plus H squared plus 4.9 X squared all over H. Hopefully you guys see what's happening here. H, whoops, limit as H approaches 0. Minus 4.9 X squared plus minus 9.6. I'm sorry, 9.8 minus 9.8 XH minus 4.9 H squared plus 4.9 X squared all over H. So we still have to get rid of that H on the bottom, right? We're getting closer. If you guys take a look, there's a minus 4.9 X squared up front and there's a positive one in the back. This now reduces to the limit as H approaches 0 of negative 9.8 XH minus 4.9 H squared all over H. I think you guys see what's going on here now. Limit as H approaches 0. Everything on the top has an H in it, so H minus 9.8 X minus 4.9 H all over H. H's cancel. limit as h approaches 0 of negative 9.8x minus 4.9h, negative 9.8x. This right here, so s prime of x is equal to negative 9.8. Got it? Okay, so now that we have this, right, now we get to find, I know this is really long, s prime of 1, okay? So then s prime of 1 means I get to plug it into, let me actually write it out first of all. So s prime of x is equal to negative 9.8. So then therefore, s prime of 1 is equal to, or 9.8x, would be negative 9.8 times 1, which is just negative 9.8. Okay, this says that at 1 second, the velocity of my bowling ball is negative 9.8 meters per second. So at 1 second, the velocity is negative 9.8 meters per second. Okay, this doesn't change anything that we learned from before. Okay, absolutely nothing. Okay, it's just now we get an expression, we get an s prime of x, we get an equation. Okay, now the next bit, find and interpret s double prime of 1. So we know that this is now going to be a of 1. We know that what we're talking about here is the acceleration of my bowling ball. Okay, which means I need to take the derivative of this thing right here. Right, so again, s double prime of x is the limit as h approaches 0 of s prime of x plus h minus s prime of x all over h. And that's going to be equal to negative 9.8 x plus h minus 9, minus a minus 9.8, sorry, x here, all over h. Okay, and let me go ahead and go down here, equal to the limit. H goes to 0. Negative 9.8 x minus 9.8 h plus 9.8 x all over h. Again, look what happens. So there's a positive 1 in the back, negative 1 up front. Limit as h approaches 0 of negative 9.8 h over h. This one's a little simpler. The h's cancel out much easier. Okay. And I get left with the limit as h approaches 0 of negative 9.8, which is just 9.8, negative 9.8. So this tells me, notice that it doesn't matter what my time is, my acceleration for this thing is always going to be negative 9.8. So at 1 second, the acceleration is negative 9.8 meters per second squared. Okay, this is telling me that the velocity of my bowling ball is changing by 9.8 meters per second every second. So it is falling downward faster. Okay. Wild stuff, huh? Okay. So Like I said, some of these problems have a lot of work behind them. Do not hesitate to come to my office hours to double check work. I am more than happy to double check your arithmetic if something went wrong. I can tell you if you went wrong, okay? These problems are long, very long, okay? It is not unheard of to turn your paper sideways so you can have more space, okay? Use up as much paper as you need. Don't do too many steps in your head. That's usually something that really leads people astray. So write down everything. Don't try to do too much in your head. Double check everything, okay? That concludes section 3.2. If you guys have any questions on the stuff that's here, come visit me at my lab hours or my office hours, or give me an email and we'll set up something outside of whatever schedule, okay? I'll see you guys around.